Okay, we've got a couple of things to do. Small number of loose ends at the end of this chapter. A couple of definitions to get through. And then we'll move on to chapter 5 on thermodynamics. So, we mentioned this briefly as part of the dissolution process. There's a thing called diffusion. And diffusion is important in chemistry because it's the underlying reason why so many of the outward-facing physical properties of matter exist. There are times when you look at the behavior of a chemical and you think, well, that's really special. I wonder how it got to be pre-programmed that way. And then you figure out, oh, it was just diffusion. And diffusion is really, really simply probability. Diffusion is the tendency of solute to move away from areas where it is in high concentration. This pen's not going to last another word. Nope. Come on, let's leave it. Sorry. Two areas of low concentration. Okay? So, from the outside, this looks like some great driving force that things are moving, that the solute is moving from one place to another, and that would have to have some, some driving force behind it. And the answer is no, not at all, not at all. This is just simple probability. It is evening out the probability of you finding it in that state. And in fact, all that we teach you in general chemistry is just the fundamentals. And then as you go and you get into the 3,000, 4,000 level class, we've got a 4,000 level class in chemistry that is 2/3 statistics. That the probability of you being this exceeds the probability of you being that, therefore you are this. We see diffusion happen this way. If I have a beaker and it's got water in it, and I put a droplet of food coloring into that beaker, only takes a couple of minutes, but that droplet disperses. And if you do this right, you'll actually see traces of the color dispersing in. Now, what's happening is that at room temperature, there is enough energy inside this system that the the energy at room temperature, ambient temperature, we're going to associate that with kinetic energy, the energy associated with motion. The water particles are going to warm up, and as they warm up, they rise, convection currents. You learned that in middle school science. And then when they get to the top, they'll rise back down. So there's going to be these convection currents going around, up and down, up and down. And they're just going to drag the particles with them. Okay. Now this has to do with probability. That if I'm still on the lookout to do this right, what I need, I couldn't find it on Amazon. What I need are really small plastic balls of different colors, just really two colors, like yellows or reds or greens and white, whatever. We're looking at Walmart for a while, couldn't find them. But if I gave you a box, and this side of the box contained black spheres, and this side of the box contained blue spheres, and I said, shake the box. Shaking the box is the same as adding kinetic energy. Then what happens is these all intermingle, right? Okay. So if I did this experiment twice with two different candidates, I brought one person up, and at the beginning, their little hard plastic balls were separated by color. And I said, shake it, and you get those balls to disperse. And then the second person comes to the front of the room, their balls are already dispersed, evenly matched. And I said, shake it and keep shaking until this happens. How long do you think that the second person has to shake the box? They're going to be shaking forever. You will never take something that is randomly organized and turn it back into something that is organized. Oh, this is far too organized. Let's actually do it really at random. Okay, these are two states. This one is much, much more probable. This one is improbable. It is improbable because this arrangement can only happen once. There is only one permutation for this, that everything black is on the left and everything blue is on the right. That can only happen one time. There are millions of different possibilities for this. So the cause of diffusion is just probability. And this probability that leads to disorder is called entropy. So diffusion is an entropic effect. It happens because nature would rather have you be disorganized, not because it wants it, but because it's just statistically more probable. And so we see these things from the outside and we think, oh, there has to be a reason for that. And the reason is just simply, it's more convenient, it's more likely. This is unlikely. Somebody, and when I do finally get a box and put the little dots in it, somebody has to put in effort to make this. This one requires no effort at all. It just naturally happens, okay? So things drift in the universe towards high entropy, high disorder. And diffusion aids that, okay? So we start with our solute in high concentration, that is very low entropy, a high amount of order, and then it just naturally ends up being disordered. Okay. Well, there's a second type of diffusion, and this one is special. This one's called osmosis. And in osmosis, two things are different. One is that it's not the solute that's moving, it's the solvent. And because osmosis is largely observed in biological systems, we're going to limit our solvent to water. Okay. So in osmosis, it's the water that moves, not the solute. And the second thing that's different is that there is a barrier. And this barrier lets some things through and blocks other things. So it's called a semi-permeable membrane. Okay. So we see this inside biological cells. The big one that people know about are red blood cells. Red blood cells are kind of lozenge shaped. They have a contour. They're like donuts, but without the hole. The hole is just a dimple. And so inside that cell, there's a little biological system, and it's floating in its own salt water. And then outside of the cell is your blood serum, which is also salty water. And if the balance of salt on the outside is different than the balance of salt on the inside, this wants to happen. This wants to happen to make the concentration of the salty water inside the cell be the same as the concentration of the water outside the cell. We call that situation isotonic, that the concentration inside the cell and outside the cell are the same. But instead of the salt moving from one place to the other, what we get instead is that the water moves either from outside the cell to inside the cell, which would blow the cell up if the concentration of salt is inside the cell is larger than the concentration of salt outside. Now, the concentration of salt inside the cell is not likely to change on its own. What's likely to change is, did you just run a lot and sweat? Because if you sweat, we talked about this a couple of weeks ago, if you sweat a lot, you lose salt. So now there's less salt in your blood serum, which means it feels like there's more water. And there's more salt inside your blood cells, so the water pushes inside your blood cell and swells those up. So there's all sorts of things, biological ramifications to over-exercising.
So reverse osmosis.
Oh, reverse, okay. Mm-hmm.
Water treatment.
Yeah, so there's a
water treatment.
There's a water treatment that you can get for your house called reverse osmosis, which is a little ceramic filter, and it's just going to force. So you now need an external force to overcome the natural tendency of entropy to fix things, and it will push the water from being in a higher salt environment to being in a lower salt environment, doing the reverse of what it's supposed to do. But you need an external force to do that.
That be pressure?
Yeah. So you've got to have a little pump in there or something. Okay. We're done with solutions. Let's Let's look at some thermodynamics. Thermodynamics literally means thermo is heat and dynamic is movement. This is the branch of science that asks, where did the energy go? Where did the heat energy go? Okay. So you know that we have two top forms of energy. And you were probably told at some point, middle school, that energy can be divided into potential energy and kinetic energy, and the kinetic energy is the energy associated with motion, and the potential is the energy associated with position. Okay. And the example everybody gives in high school is you take a ball and you throw the ball in the air, and it loses potential energy on the way up, and then it gains it coming back down again. And there's a change in kinetic, and the kinetic and potential are always in balance, which is great for high school physics. It's a little bit more complicated than that in chemistry. Kinetic energy is still the energy associated with motion. Heat energy puts our particles, our atoms, gases, molecules, whatever it is that we're looking at, into motion. So that kinetic energy is associated with heat. Potential energy is locked into chemical bonds. And if we do reactions that make new chemical bonds, then we kind of trap potential energy into those bonds. If we do reactions that break chemical bonds, then we release the energy that are in those bonds. Most reactions do a little bit of both, that you'll be breaking something over here and then moving that around and then reattaching it somewhere else. So we're going to break some bonds and then make some other new bonds, which means we can never really know until we do it whether our reaction is going to give out heat or take in heat as it progresses. Okay. So if energy is locked into bonds and we put more energy in if we make new bonds and get energy out if we break those bonds, getting the energy out is going to be in the form of heat. So these two can be converted into each other. Potential energy can be converted into heat energy. And we're going to have two possible reaction outcomes. They are called endothermic and exothermic. Okay. If I plot energy versus time for an endothermic reaction. Endothermic reactions take in heat as it progresses. Okay, let's have a think. This reaction is going to take in heat. This is our scale for energy, and this is our scale for time. I've got a reactant, then an arrow, then a product. So on the time scale, reactants are here, product is here, okay? If this reaction takes in heat as it progresses, where on this scale am I going to write my reactants? Down here at the bottom, somewhere in the middle, or at the top?
Kind of like a sine wave.
Okay.
So,
It's going to take in heat. The reactants are going to be lower in energy than the product is. So right now, this is all I know. This week's lab exercise is called Endo-Exo, and we're going to give you two reactions. We're going to put the little computerized thermometers inside the test tube and give you two reactions. It might be in a beaker, I don't remember. And one of them is going to take in heat as it goes. It's going to get warmer. And the other one, no, that's a lie. The other one is going to give out energy, and that will get warmer. And one of them is going to take in heat from its surroundings, which means it will physically get colder. Right now, this is all I know. I start with the reactant, I end with the product. The product is higher in energy than the reactant was because this took in heat as it progressed. The question gets to be, what's between here and here? Because if what's between here and here is just a straight line, I wouldn't write this down. If all that's here is a straight line, I think my common sense will say that that's not true. If this is just a straight line, then what would happen is the reactant would take in heat, turn into the product, and then there's no barrier to stop that product from giving the heat back out again. So it would just turn back into the reactant. It would be like rolling a ball up a hill. The ball rolls up the hill while you keep trying. But as soon as you stop trying, the ball would roll back down the hill again. So this is not the shape that is between here and here. There's a barrier that stops the back from rolling back down. That's where that funny shape.
parabola,
said.
the sine wave, yeah.
There's a hump. There is a hump, and then it flattens out. So there are two things to read. from this graph. One is the big energy gap. That gap is labeled EA. That's a capital E, E for energy, and a lowercase a for activation. EA is the activation energy. That is a barrier. Below which reaction cannot occur. Almost out of that pencil. Okay. How much does it cost to get into Disney World? How much is a ticket to get into Disney World? It is expensive. So expensive, they don't reveal the price on their website. It's $109 a day. It's $109 to get into Disney World. If you show up at the gates with $108, do you get in? No. That's your activation energy. Giving this reaction some energy to initiate the reaction is not going to be good enough. It needs $109 worth of energy. At $109, this reaction happens. Now look, it doesn't actually spend $109 because it gives you some change. It comes back down at the end. But this gap is less than the gap that they told you. So this is like buying a pair of shoes with your credit card and then getting 3% cash back or whatever it is on your credit card. Right? But you have to spend the money first, and then they give you something back. This second value is the change in heat. Our symbol for heat is going to be an H, and it's the change. And changes in science are represented by the symbol delta. Delta either as a capital, which means change, or delta as the lowercase delta, which means, yes, it's still a change, but it's only a small one. Delta H is our enthalpy change. Enthalpy is the German word for heat. And over the course of time, we are all going to get tired of calling it enthalpy change, and I'm going to start calling it enthalpy, which is the wrong thing to do. Nobody, and I mean nobody, is interested in finding how much enthalpy something has. We're only interested in how much enthalpy changes. That's the amount of heat that either goes in or comes out. For a reaction that takes in heat, delta H is going to have positive values. My symbol for positive is a plus VE. Positive values of delta H. So enthalpy is an energy. What do we measure energy in? Joules. This is going to be big enough that we can measure it with a thermometer. So these are going to be in kilojoules. That is an endothermic reaction. Okay. Exact opposite. Exact opposite is going to be an exothermic reaction, where the product is lower in energy than the reactant. Again, there's a hump. That's our activation energy. And sometimes the activation energies are really tall, and sometimes they're just little things. And then there is a gap. Activation energy goes this way, and delta H goes that way. Okay, this is a good time to reiterate that energies have a magnitude. There is a number that we're going to measure in kilojoules, and they have a direction, in or out, plus or minus. The delta H for an exothermic reaction has negative values. That heat is given away. It is negative value. Okay. Now, some reactions can be highly exothermic. I'm going to show you one right now. But we're not worried about them because all of our reactions need an activation energy. So reactions that are going to give you out heat, they don't happen spontaneously. You have to give them a nudge. Like even something like fireworks, which they're explosive. They're explosively exothermic. The fireworks don't catch fire in the trunk of your car as you're driving them back from the fireworks stand. You have to set fire to them before they explode. You have to put in something, and then you get all of this back. So for an exothermic, you put in a little bit of heat, you immediately get that heat back, and then you get all of this extra heat as well. Okay? Okay. Oh, I brought a couple of things from upstairs. What's that? It's been written on the board a couple of times, and I keep saying I'll have to go upstairs and get one. This is a volumetric flask. It's got an incredibly fine scribed line right there. And when the meniscus of your solution touches that line, it is exactly 250 milliliters. Okay, bulb, and then a long neck. The long neck means we can use we can squeeze the volume down to get a more precision in reading that.
Graduation marks.
This only has one graduation mark, and it's 250 milliliters, plus or minus, it'll tell you on the vessel, plus or minus 0.12 milliliters at 25 degrees Celsius at room temperature. So that's pretty accurate.
That's the standard unit that we would use for water in a solution, would be the 250 milliliters.
These come in all different sizes. If you go upstairs and look in our lab, we've got them in all different varieties, but we'll have 200s, we'll have 125s, we'll have 500s, 400s, and then liters, and then 2 liters. You can't get one that says 160 milliliters. Right? It goes in sensible intervals. This is a graduated cylinder. This is measured in milliliters, but there's a gap between those milliliters, so you can guess what the decimal is. This is 2-propanol, also known as isopropyl alcohol, also known as rubbing alcohol. And I'm going to pour out about 20 milliliters. I'm going to pour it in a jug. And then, it's only a little bit, look, it barely coats the bottom of the flask. And if I turn it around, I can get it just about so that it coats the outside, the inside walls of the flask, okay? What I'm doing now is just allowing the vapor from the alcohol to fill up enough of the airspace inside the bottle. Turning it completely up, none of it is running to the bottom. So this is like really, really small amount of alcohol. Okay. Now I'm going to set it on fire. You always have to look up to make sure you're not immediately underneath the smoke detector. I forgot to put my safety glasses on. That tiny bit of alcohol mixed with air. And then we did a lot of exchanging of chemical bonds. A lot of exchanging of chemical bonds. That alcohol has 3 carbons, let me think, 8 hydrogens, and 1 oxygen. And I just turned that alcohol plus a whole bunch of, pass that around, plus a whole bunch of oxygen into carbon dioxide and water. What's special about the jug? It's warm. Yeah, I mean, I think we can obviously tell, but you would not want to put your hand over that flame.
It's also foggy, like.
Yeah, so that's water vapor.
Yeah. After you take a shower or something.
Mm-hmm. That's called a whoosh bottle. Apt for Concordia. What I just did, what type of reaction would that be? I took alcohol and I burned it.
Endothermic.
Oh, well, so I can take one of these two. Did it give out heat or take in heat?
No, it gave out heat.
It gave out heat, right? It was warm to the touch. It probably still is a little bit warm.
Yeah.
Yeah, it's still warm. This is exothermic. What class of reaction was that? Remember, we did a couple of different types of reaction. That's a combustion. And combustions were all types of the same. They're all basically additions. Like all combustions, all of them are exothermic. When we burn stuff, it releases the heat. Okay, I took the chemical potential energy that was in the carbon to carbon and carbon to hydrogen bonds, and then switched them around. And I added oxygen to hydrogen bonds and carbon to oxygen bonds. Okay. So at the end, I've got a whole new set of bonds at the beginning than I did at the beginning. And you can actually sit with a piece of paper and a textbook where the bond energies of each of the things that we just disrupted are in the textbook, and calculate, oh, this gave out so much energy. You can actually figure that out because it's all been tabulated. Our product is much lower in energy than the reactant was. I mean, I think you could tell by the ferocity of that flame that was quite a big gap. And yet, that fire was never going to happen on its own. That required me to just give it a bit of a nudge. Do you ever follow a gasoline tanker on the highway? You ever worried that, fireball? When is the gasoline tanker the most dangerous? When it's full or when it's empty?
When it's almost empty.
When it's practically empty, yeah. Because you don't just need the gasoline, you need oxygen for a combustion. You need three things to cause a fire. You need the fuel, you need the oxygen, and you need a source of ignition. And without any one of those three, you're safe. So you can have the tanker full of gasoline. And when it's full, it's actually at its safest because there's no oxygen inside the tank. When it's right up to the brim, that's the safest it's going to be. If it's half full, or it's coming home and it's empty, but there's still gas vapor in there, now it's dangerous. Because something as simple as the static electricity spark from you wearing synthetic clothes, and when you get out of the car and you touch the car, you discharge that static, you get that one little spark of static. That's enough to start a fire. Yeah, so the gas tankers are the most dangerous when they're empty, not when they're full. Okay. If I change the fuel, because the one that I used was isopropyl alcohol. If I used just regular alcohol or I used a small alcohol called methanol, then the fireball is different. You get a different kind of fireball than you do with that one. This one's more determined. It carries more heat, and the nozzle, the jet engine nozzle at the top is larger. The other ones do more of they cause a fireball that then causes kind of a vacuum underneath it, and you get a woof.
This is a gas pump. It's like may contain up to 10% ethanol.
Mm-hmm. Gasoline does have ethanol in it.
Yeah, which is an alcohol, right?
Mm-hmm.
Yeah.
See, the good thing about alcohols is they're incredibly easy to make. Incredibly easy to make. Nature wants alcohols to be made. How do you make alcohol?
Fermentation.
Okay, what do you need to go into the fermentation process?
Some sort of reactant like yeast or...
So yeast is a thing.
Yeah. But when it combines with...
And water, because it's in solution. And
heat.
What's the other thing? What does the yeast work on? Yeast converts something into alcohol. Sugar. So if you've got sugary water and yeast, that will just automatically start turning into alcohol.
That's why when bread rises, if you've ever made homemade bread, it can have this kind of feel.
Bread smell, that really nice smell of baking bread, do you know what that smell is? That's alcohol. That's the same. If you got to Fort Worth, as you pass the Mrs. Baird's bread, factory, it smells like alcohol. And you know what's right next to the Mrs. Baird's bread? The Miller Brewery on 35 as you go through Fort Worth. And going north, you hit the bread before you hit the brewery. And coming south, you hit the brewery before you hit the bread. And you can't tell which way you're traveling from the smell, because the smell is the same from both factories. That's the same smell. Nature has found that alcohols are a little stable molecule. And we need yeast, and we need sugar, and we need water. Where has nature put the sugary water?
And plants.
Which kind of plants?
All plants.
Some more than others.
But yeah, but like, okay, if we're making wine, it'd be grapes.
Nature has put the sugary water inside fruit, specifically grapes, because let's do that. Where has nature put the yeast?
The fungus. Or
Where has nature put it?
outside of that, it's
On the skin of the grape.
okay. Interesting.
Guess how you make alcohol?
Just let it sit.
You squish the grape.
Oh, yeah.
The yeast touches the sugary water, and boom, you have alcohol straight away. It starts straight away. This biological process is going to start straight away. Anybody ever been in prison? Don't answer that question. How difficult is it for prisons to keep alcohol away from their inmates? It's insanely difficult for prisons to keep alcohol away from their inmates, because we give them access to water and we let them have sugar. And you can find yeast anywhere. So you can make alcohol in a garbage bag with a slice of bread and some fruit juice. Yeah, it's not great. Nobody said it was going to be great, but nobody drinks alcohol because they enjoy the taste, right? Okay, let's see what we're going to talk about. So the next thing that is up, I think, is a discussion of magnitudes. Oh, I know what we could do. Before we get to the magnitudes, we're going to talk about how do I measure it? We'll leave that for another day. Okay. So next, we're going to talk about how do I measure that heat? That's something called calorimetry. And then once we know that we can measure heat, then it's calculation, different type of calculations. Okay? The remainder of this chapter is math. Brace yourselves. It's only adding and subtracting. That's all it is. We're going to take a bunch of numbers and add them up, and then subtract them from another bunch of numbers that we've added up.
So we have not read logs yet.
Nope. Logs only show up one time.
I have a question for you.